In this video, we're going to begin our study of the concept of derivative. What we're going to see its precise definition and how we can interpret it geometrically and in terms of velocities. Okay, so if we have a function that is indicating the distance of an object f from a fixed starting point at time x, its average speed on the interval ab can be written as, well, f of b minus f of a over b minus a, right? That's the average velocity. So here you can see, well, we're changing the velocity, and to find the instantaneous speed of the object at the point A, what we need to do is we need to get a better approximation of my average velocity by taking b closer to A. So by moving here my point B and making it closer and closer to A, what I'm doing is getting a better approximation of the instant velocity at that point. Perfect. So how can we interpret this geometrically? As you saw here, I was drawing this curve and we're moving the point B, and there was a line that was moving along. It was this line that was connecting the point A f of A to the point B f of B. And that line has a name and is going to give us the geometric interpretation of the derivative. So if we have a function and A is less than B, the unique straight line that passes through the points A f of A and B f of B is called the secant line from A to B, which is exactly what we saw. And the slope of this line is just f of B minus f of A over b minus a. That coincides with the idea of the average velocity. And again, if we move b closer and closer to a, what would happen is that in the limit, as you see here, I'm getting closer and closer, we end up with the tangent line to the curve. So the limit as b approaches a of f of b minus f of a over b minus a, as b approaches a, is going to give us the slope of the tangent line to my curve at the point a f of a. So that is the geometric interpretation. The derivative is the slope of the tangent line to the graph of the function at the point a f of a. So with that in mind, let's write down the definition. Well, we have a function and we have a number a that is in the domain. We say that f is differentiable at a if the limit as x approaches a of f of x minus f of a over x minus a exists. And if the limit exists, we call it the derivative of a f at a, and we denote it by f prime of a. Notice that if we write x as a plus h for some small h, when x approaches a, that's the same as saying that h approaches 0. So we can also write a definition of the derivative of f prime of a is equal to what I said before, the limit as x approaches a of f of x minus f of a over x minus a, but we can also write it as the limit as h approaches 0 of f of a plus h minus f of a over h. Both of them are correct. Both of them are very helpful. Sometimes we're going to use one version, sometimes we're going to use a different version. In some cases, one is a bit easier to work with than the other. Most of the time, they're pretty much the same. Okay, so now I want to find our first derivative using the definition. So we're going to find the derivative of f of x is equal to x squared. I'm pretty sure you're telling me now, oh my gosh, you know it's going to be 2x. We all know that the derivative of x squared is 2x. Yeah, we do know it, but now we have to write down a proof using the definition. So from the definition, we know that f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. Here, f of x is x squared, so this becomes just the limit as x approaches a of x squared minus a squared over x minus a. Now we can factor this into x squared minus a squared is just x plus a times x minus a. And here we see that some nice cancellation happened. So we end up with the limit as x approaches a of x plus a. Oh, brilliant. This is 2a. Exactly what you told me this was going to be.